that they were living. I mean, the migration. I understand what you're saying. This is a complete shift in my perception of how salmon live. That they are actually like I live right next to a salmon stream in Crescent City, California, and the fish actually migrate out to the ocean. They don't migrate up to spawn. This is great. Thank you.
Well, great. Glad that I can talk to you as a biologist, and we can share some thoughts about that. Yeah, I mean, they have to get back to spawn, and according to the physiologist William Hoare, who I was reading when I was back in graduate school, you can tell that the salmon almost certainly evolved originally in fresh water. Essentially, they're a rainbow trout,
right.
And because they have a kidney that's most appropriate for a freshwater fish. And during the periods of glacial advance and retreat, there presumably was a large evolutionary advantage for those organisms that could migrate and go to new streams and then, but they have very, very stringent requirements for spawning. I was always interested that when they lost the Upper Adams River sockeye, for example, when they lost that particular genetic strain of fish, and then they took the dam out that had caused the loss of the fish, and they had tried to take lower Adams River sockeye salmon and reinstall them into Upper Adams River, and they never took because they never had the right genes.
Mm-hmm.
And you can go on Vancouver Island, and you can go to Little Qualicum River, and then you can go to, I think it's called Black Creek, just north of it. And they're completely different environments. And the salmon that live in this case, silver salmon, that live in these two environments are completely different creatures. The Little Qualicum have to be able to do well in cold oligotrophic waters, and the Black Creek salmon have to do well in warm, very nutrient-rich and plant and animal-rich environments. And yet they both do fine in their particular environments, and they are very specially adapted to their environments. And so when they put in a big hatchery at Qualicum River, and a lot of those salmon drifted into these small creeks, there was a great deal of concern of diluting the beautifully fine-tuned genetic stocks of the individual creek salmon.
Right.
We could talk about salmon all this time, but let's get on.
Well, I want to. You mentioned the AROI, and this reminds me of something that I just read not very long ago, and it makes sense, but it still was I thought really interesting. I was reading some work on plants, and plants we can argue about the word predict. I like the word predict, but if you don't like it, then we can just ignore that.
I'm okay with it. I'm a modeler. I sometimes predict.
Well, I'm thinking, plants predict is the point. That I was reading that plants in the understory grow branches by how the overstory is going to look by the time the branch gets out to where it will be able to be fully functional at receiving energy through photosynthesis. And
sure.
I thought that was really interesting because we normally, the point is that plants are working on the EROI as well.
Absolutely. I'm looking out. I live on the shore of Flathead Lake in Montana, and I'm looking out through a pine forest, and I can see on one side of a pine tree branches that go all the way down to the bottom, and on the other side, where it's growing next to another pine tree, the branches are not there in the lower part of the pine tree. And you go there and you can find the dead branches or the little holes where the branches once were, but the tree, now I don't know whether the tree makes a decision or the branch just deals with the net, but it's expensive to have a branch, and a tree will maintain that branch only if it has a positive energy return on investment, the investment being investing into the leaves and the needles and the branches and all of the incredible chemistry and biochemistry and stuff that the branch does. But if the branch is not carrying its weight, and in a branch like an animal, at night and during the daytime too, uses energy. It takes energy to maintain its structure, to maintain itself. It's called maintenance metabolism. And if a branch can't pay for its maintenance metabolism because it doesn't get enough weight, then it's goodbye branch. Now, whether they can anticipate or not, I don't know about that. That's a new one for me. But I wouldn't be surprised.
Yeah, if you want, I can send you the source later.
Sure.
But anyway, so how does this apply to a society? This concept.
Yeah, and I'd just like to make one point that if anybody wants to Google my name, Charles Hall, and then Tyee, all of this stuff was written up particularly well by that magazine in British Columbia.
Okay, great.
Okay, so how did I get involved in applying this to oil and uranium and other sorts of things? Well, as I said, my advisor, Howard Odom, had got me thinking that way, and I had this really good undergraduate student. At the time, I was a professor at Cornell University, and I had a really promising undergraduate named Cutler Cleveland, and who's now made quite a name for himself in the energy world. But he came to me and said that he wanted to do a project with me, and we talked about various things, and so we decided he told me that he thought he was really more interested in energy than simply environment or ecology, and at that time I was an ecology professor. And so I said, well, let's re-look at the Hubbard curve, and that led to us doing a paper that's called, oh gosh, I can't remember the title of it, but something like, wait a minute, I might have it right here. But that went to us looking at, I think I just found it. It was called Petroleum Drilling and Production in the United States, Yield per Effort and Net Energy Analysis. And what we did, we went back and looked at the Hubbard data. And this is published.
People might not know what that means.
Oh, the Hubbard data means how many barrels of oil you gain in the United States from drilling a foot in looking for it. This guy, Marion King Hubbard, was the originator of all of this kind of work. I'm old enough to have known him reasonably well at one time. And he famously predicted in 1955 that the United States would have a peak in oil production in 1970, and everybody shunned him and called him bad names and said he was a terrible scientist and so forth. But in fact, the United States did predict in 1970 we have never produced as much oil. Even now, with a little uptick recently, we have never produced or extracted as much oil as we did in 1970. So we took the Hubbard idea of yield per effort and how many barrels you get per foot drilled and updated his data, and we found a very strange pattern that it declined as Hubbard had observed. We were getting less oil for each foot we drilled looking for it, but then it went up, and then it went back down, and over a period of about 10 years, and this was very confusing to us. And then I remember Cutler plotting the data, and I just come back from giving my fisheries lecture in ecology, and Cutler said, look, this data, it doesn't make any sense, but it's very clear. And I looked at it, and I scratched my head, and I didn't know what. And then all of a sudden, I thought about my lecture. And at that time, Cutler was a great, big, muscular fellow, a great athlete. And I got so excited, I pounded on his shoulder with such force that I left black and blue marks. I was so excited. And I said, look at this, Cutler. It's just like for fisheries. The harder you fish, that is, the more feet you drill for oil, the less you get per foot. your yield per effort is lower at greater effort. And, this is in economics, although economists don't talk about it very much, it's decreasing marginal return. And Ricardo, way back 200 years ago, wrote about this. But basically what it means is those people who say drill, 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 the data doesn't support what they say, at least so far, because the more you drill, the less efficiently you drill, and the lower your return per effort. And that's what we found. So we started analyzing things instead of the feet you use for drilling, the energy you use for drilling, and ultimately applied this energy return on an investment concept to getting oil out of the ground.
So they were basically measuring it by feet as opposed to measuring it by energy invested is
right.
Sort of like measuring what miles you get per amount of time you drive versus the amount of distance you drive. And my point is that they were kind of measuring the wrong input.
Well, it wasn't wrong exactly, but I think it's more meaningful. All kinds of things are more meaningful when you start looking at the energy investment. Well, I see what you mean. Like with the salmon, you might talk about how many miles did the salmon swim, but of greater interest, I think, biologically, is how much energy did it use for the salmon to swim from point A to point B.
Right, because if they're going straight uphill the whole time, that takes a lot more energy than if it's fairly flat.
Yeah, of course. Yep.
So, what are the implications of what you're saying? Of the last bit you're saying, what were the implications of that for the oil economy?
Well, if you plot the growth of the world economy, it's almost exactly the same curve as the growth of our use of fossil fuels. I remember hearing the mayor of Denver once say that the Sioux Indians that used to live there were completely dependent upon the bison for everything they ate, everything they lived in, everything they wore, their tools, their weapons, and so forth were all based on the bison. And they celebrated it and did dances and had special feasts and so forth in terms of the bison. And he said today, Denver is completely dependent upon oil, and not only do we not celebrate it, people don't even pay any attention to it. They think it's technology, but it drives me nuts. People are talking all the time about all this wondrous technology, but almost all of that technology is dependent directly or indirectly upon having cheap energy. And how long will we have cheap energy? Well, if you plot from the end of the Great Depression till today, you'll find that the growth of the U.S. economy has declined essentially every decade, from 5% to 3% to 2% to 1% to less than 1% today. That's the growth of the U.S. economy, and in fact, of most OECD or Western economies, it's the same thing. We basically stopped growing. Europe has basically stopped growing. Japan has basically stopped growing. U.S., we can argue about it, but it certainly doesn't grow like it used to, and probably not in real terms or inflation-corrected terms as much as 1% a year. And that's the same curve as you get from plotting the global production of oil. We used to grow. I think we could grow very much because we had a lot of energy. Economic production is a work process. Any work process requires energy. Oil is the best form of energy in all kinds of ways. And it's becoming less abundant, and I think it's happening right now. You look around, and our great universities are broke often. Most of our states are either broke or have cut back on the services they've offered enormously. Many pension plans are broke. Everybody's broke except the 1%, I guess. And so what's happening is that we have, I think, the impact of a restriction in the amount of oil